let's start with the thermodynamic arguments before we get anything else. And in all these cases, we're going to be looking at mercury electrodes and in simple electrolytic solutions, because once we get beyond mercury and simple electrolytic solutions, there's really no good theory for that. So we're talking about mercury in solution, and mostly aqueous solutions was some of the earliest work, but now a lot of work has actually been done in non-aqueous solvents, particularly for those solvents that are useful for electrochemical measurements, such as acetonitrile, dimethylformamide, and so on. We might start out with mercury in KCl as a good place to start. Remember, that was a prototype electrode that's so-called ideally polarized over quite a wide range. We don't see any charge leakage across from Faradaic response, and it seems to be a good model for an electrified interface that does not support Faradaic reactions over a good several hundreds of millivolts of potential. Now, if we take KCl and just have a solution of KCl in a beaker, if we sit in the middle of that beaker and we look all around us, it's isotropic. There's no change in the concentration of potassium ions in any particular direction. There's no change in chloride ions concentration in any particular direction. Any way we look, KCl is isotropic system. Now, however, if we put a mercury electrode in that system, now we have a situation in which we can introduce an anisotropic part of the solution. The solution will become more ordered at that electrode interface, and so we've reduced entropy locally because we've got an additional energy source. We've got that surface tension, surface energy of the mercury electrode that is able to reduce the entropy locally. So we can actually make the local region around the electrode more ordered than it would otherwise be by adding the surface tension energy. And so the trick is to see if we can measure that surface tension and see something about the ordering of molecules at the electrode surface. So what happens? Well, at the mercury electrode, the water molecules become adsorbed. And notice we're using the word add and not ab. So we're talking about adsorbed, which means we're stuck onto something rather than being stuck into something. And so molecules being adsorbed suggests initially that they're just sort of stuck right to the surface, but in fact we use the word adsorbed in chemistry and in physical chemistry particularly to indicate the fact that there's more water molecules there than there would otherwise be there. All right, so there's an absorbed amount. Chloride ions are going to be absorbed and potassium ions are going to be absorbed. How can we find out how much of any of those are absorbed? That's the real tricky question that we're going to ask ourselves. Now, when we put that mercury electrode in the KCl, we can do it in such a way that no charge gets passed at the interface. No charge gets passed between the electrode and the interface. It can't be passed because the mercury electrode is an ideally polarized electrode. It does not allow that charge to pass. So if we now have an electrode, mercury electrode that's in solution, and we have some adsorbed ions and water molecules at it, that implies that there must now be a charge separation, because we can't let charge pass from the electrode to the solution, and since now more ions are present at the interface than there was otherwise be there is a buildup of charge at the interface, there's a buildup of charge on the water, or on the mercury, there's a charge separation. The question is, what is that amount of charge? So that's really what we're interested in. Remember we talked about initially that the amount of charge on the metal has to be equal to the amount of charge in the solution. And in fact, we'll use sigmas a lot of times here to refer to the same thing, which are just the charge density. And that would typically, a lot of times people would report that in microcoulombs per square centimeter, because that's a convenient amount. Turns out that's basically how much we're going to be seeing for charge in that region of microcoulombs. So at the interface, we're going to have some ions adsorbed. We're going to have dipoles that are oriented at the interface. They're not randomly around in solution. They're going to be now oriented to the interface, perhaps pointing to the interface, perhaps pointing the other direction from the interface, or maybe just in this way at the interface. And also, because the metal is charged, we have materials that may not necessarily be dipoles in bulk, but because they've got some charge, the ability to shift the charge around in the molecule, they may become induced dipoles. So molecules that are normally spherical and have a spherical charge distribution now may have a dipole because of the charge on the metal induces that dipole. So let's talk about, for most of the next few pages, this particular cell where we have mercury, chloride ion, some species M, and then we have our reference electrode, silver chloride. And so we'll call M our modifier. We can think about potassium chloride alone, and then we can think about what happens when we add M to it. And that'll be a probe. We can start with potassium chloride and then change M and see what happens. Our goal here is to see if we can measure the change in surface tension as a function of these various quantities: the concentration of potassium ions, concentration of chloride ions, concentration of the modifier, the electrode potential, the external temperature, and the external pressure. And in fact, we're not really usually talking about concentration, we're talking about activities, but we'll talk about concentrations to make it simple. How can we measure the surface tension of the mercury? Well, it turns out it's not as hard as it looks. We can use a method that's very old now, using a dropping mercury electrode. In fact, this is what Hairovsky was trying to do when he invented the dropping mercury electrode. Although we've used it for many years now for analytical purposes, its first use was for actually measuring surface tensions. And the idea was that we'd have a reservoir of mercury and in a solution of some sort. Applied a potential to it versus a reference electrode. We change the potential on our mercury. What happens? Well, when we change the potential of the mercury, we're changing the surface energy of the mercury. We're adding charge to it, we're removing charge to it. So by changing the surface energy, we're going to be changing the surface tension. And it turns out that Hairovsky noticed that the DME, dropping mercury electrode drop time, was in direct relationship to this surface tension. And he said T max is equal to 2 pi RC mg, where RC is the radius of the electrode capillary. Our lambda is our lambda is our surface tension. M is the mass per second. And G is the gravitational factor. And what you found is that the time between drops, or the lifetime of the drops, follows a relationship with potential like this, where there's a maximum, and that maximum we'll call E sub z, and this would be along the potential axis, and with this it's more negative. So we get this roughly parabolic shape. We don't go to more positive potentials than this because remember the mercury electrode is susceptible to being oxidized to mercury ions. So at this point we're going to be oxidizing mercury. But we can go quite negative and we see this parabolic shape. Turns out that maximum of the thing is also called a PZC, which stands for point of zero charge. And we can also there's another method I guess I put on my notes. I was just looking at it, which is was developed by a guy named Lippmann. It's an alternate way to do the same experiment. It's actually a little bit more tricky, but it's a little bit more sensitive, actually. Lippmann said, let's, instead of waiting for drops to fall, let's just balance exactly out the force it takes to hold the drop from falling. So that's a null measurement, actually fairly sensitive. So Lippmann said, let's do the same thing. We have a capillary radius, the height of the mercury, I'm not sure what D actually stands for, so I'm sorry about that. Density of mercury. And G again is the gravity. So that also is an alternate way of doing it. Turns out the Hirovsky, inventing this dropping mercury electrode for this purpose, realized the other analytical advantage of it, and so on. Now at the PZC, the charge on the metal is 0, the charge in solution is 0, and we have then a maximum in our gamma, our lambda. And as we go away from the PZC, now we start to build up a charge in the solution and in the metal, and that charge in the metal now tends to reduce the surface tension of the surface. The idea is that you've got, say, charged ions on the electrode surface those ions tend to repel each other, and that repelling of the ions weakens the surface tension and makes it less, there's less tension there. Okay. So the question is, why are we seeing this sort of behavior? Why are ions affecting the shape of this curve? And if you remember, I think we pointed this out, there is a thing called the outer Helmholtz plane. And the OHP is the locus of centers of solvated ions. In other words, we have ions that are solvated. Typically positively charged ions tend to be solvated, and they have some sort of oriented dipoles of the solvent around it. And if we think about moving this solvated ion next to the electrode surface, it actually can only get to a certain distance away. And that will depend on the dipole that's solvated to it, so water usually, and the size of the ion itself. And so there is a sort of a minimum distance for these materials to be stuck onto the electrode surface. And that outer Helmholtz plane refers to that particular distance. Since there's an outer Helmholtz plane, that implies that there's an inner Helmholtz plane. And that is the locus of unsolvated ions. In other words, we're talking about situations in which ions are lacking a solvation sheath and are now stuck directly to the electrode surface. And a lot of times these ions stuck directly to the electrode surface are anions. Chloride is an excellent example of an ion that would be often found in the inner Helmholtz plane. So there is another set of potential or plane they call IHP. The OHP depends a little bit on the ion concentrations and things like that, but under typical conditions, the OHP is about 10 angstroms away. The solvation size of the water molecule and the ion itself gives a range of about 10 angstroms. Now we can have absorption under these conditions. Now it takes a little bit of two meanings, because we can think about molecules being absorbed in the outer Helmholtz plane, or we can think about molecules being absorbed in the inner Helmholtz plane. And so we use two different words to refer to those two different types of absorption. One is what they call nonspecific absorption, and that would refer particularly to the OHP type situation, where we don't have, well, the molecule is close to the electrode surface. It's not physically touching the electrode surface. And then we have specific absorption at the inner Helmholtz plane, where we actually now have molecules directly attached to the electrode surface, or as close as feasible to the electrode surface. Now, what if we do have molecules attached to the electrode surface or nearby? Well, that suggests that there will be a potential gradient near the electrode surface, and that's an important idea. So if we think about the potential, it turns out that we often can assume that the potential has a gradient, and for ease of comparison, we'll talk about the gradient being in a straight line, although it wouldn't necessarily be in a straight line. We can assume it is. But there will be a potential drop because we've got the bulk solution potential, and then we've got a drop in potential because of these adsorbed charges on the electrode surface. And that gradient in potential will affect other electrochemistry. It turns out that that gradient of potential drop is on the order of 1 volt per angstrom, or about 10 to the 7th volts per centimeter. In other words, 10 megavolts per centimeter. So if we could blow up that region of potential drop to 1 centimeter, that'd be 10 million volts between my fingers at that particular point. So the potential gradient is quite dramatic and quite large at those surfaces. So it's expected that that large potential gradient may have some effect on the rate of electrode reactions. All right. So let's clarify some terms for later analysis. If we take our electrode and put it in solution, just before we put it in solution, or time equal to 0 as we just start putting it in solution, we can think about the concentration of species I being uniformly distributed throughout the bulk, even at the electrode surface. So again, using our hatched lines as indicating our electrode surface, concentration of I at the interface or anywhere else would be uniform, because we haven't done anything. We just put the electrode in, nothing has happened. But within a very short period of time, the concentration at the interface is expected to be quite different than it is in the bulk because of this absorption effect. And so we might see more of I at the interface than would otherwise be present. So we'd have still C sub I in the bulk, but then at a particular distance we could refer to the concentration of I at the interface, Ci prime, at a particular distance x as having some value. So C sub I x is equal to C sub I prime x minus C sub I 0. In other words, C sub I x is what we're going to call the surface excess amount of that particular material. because although there is an amount of I present at the electrode surface, what we're really interested in is the excess amount, or perhaps the decess amount, where we have increased or decreased amounts of that near the electrode surface. Not what it is in the bulk, but what the perturbation is from the bulk amount, and that would be what we call the surface excess amount. So we're subtracting off the bulk concentration there. And so C sub I 0 is our reference level. So the amount absorbed, and we're going to use the large capital letter lambda to indicate that, is equal to integrating from the electrode surface from 0 to infinity, this surface excess amount with distance. And so in other words, we're going to integrate the area under that curve, excess amount. There's another way sometimes people use it where we use number of molecules and so n sub I to the r is our reference amount, number of molecules. N sub I is the particular amount there. And n sub I to the sigma power is the surface excess amount. And the difference is simply this between the two things. N sub I divided by the area is going to be our absorption. So our free energy at the surface is, their free energy at the interface is this delta G line. Again, we're using electrochemical quantities here. Just like before, we're drawing a line over chemical potentials to make them electrochemical potentials. Here's the electrochemical free energy of the interface. It's going to be a function of the surface tension, the surface excess amount, temperature, pressure, and area. In other words, our surface tension is going to be a gradient of the surface free energy as a function of area as we maintain constant temperature, pressure, and chemical potential. So all things other being equal, what we can do is we can change the surface free energy and get our surface tension out of it. Okay. So what we're really interested in is this sort of relationship. What is the derivative of the surface tension as a function of the specifically adsorbed materials and the electrochemical free potential? And so by summing up the change in the free energy, electrochemical free energy, electrochemical potential, and the surface excess of any species present in the system, and I would refer to not only the ions and so on in the system, and say a modifier which may be charged or uncharged, water, but also would refer to electrons in the metal. Now, we'd have to go through some math here, and I'm just going to write down the result. Now, if you go back and look at the rules for the electrochemical potential and the chemical potential, you can actually derive this pretty straightforwardly. And you see that we will derive a relationship between the derivative of the surface tension that has a relationship between the charge density on the metal times the derivative of the potential plus the specific excess of potassium, and I'll explain this notation in just a second. Oops, D times the derivative of the chemical potential of potassium chloride plus the Same thing for the modifier species. And so this would be an isotherm for the KCl species. In other words, a description of the surface tension as a function of these other particular quantities. The E minus is a sort of a notation, especially in use by these particular people, to refer to the potential measured versus a reference electrode that responds to an anion. So silver chloride is an example of that. If we change the anion concentration of the silver chloride electrode, the potential will change. And so silver chloride would be an example of a reference electrode that we could refer to as E minus. Now, the reason we're using these little parentheses is that water is going to be our reference component. We really have no real tools at describing what the actual amounts of adsorbed material is at the electrode surface. So what we're going to do is refer to things as being in excess of our reference amount. So water being present in large quantities of the system is going to be a reference component. And it would be the same situation for, say, a situation in another solvent. We'd use that as a reference component. But that's what we refer to in this particular case with the parentheses. And if we write down this notation, what that really means is that we're taking the integrated surface excess of potassium ion, and we're subtracting the difference in the mole fractions of potassium chloride, or the ratio of the mole fraction of potassium chloride over the mole fraction of water, times the integrated surface excess amount of water. And this term turns out to be small under normal conditions where we have small amounts of electrolyte in the system. Usually we have a large mole fraction of water, very small mole fraction of the salt, and so this term turns out to be small enough so that usually we can ignore it in the system. So this is what we call the relative surface excess of potassium ion. Again, let's reiterate. What we've got is we're going to have some surface excess of potassium ions. Now, we're calling it excess, but it could actually be a depletion amount. In that case, that number would be negative, or an excess. And that just refers to the fact that some amount of potassium ions are going to be present at the electrode surface in excess of what we'd see in the bulk. And we're also ratioing that against what would be present say water, how much water is present. So we're ratioing it again versus the relative amount of water that would be absorbed at the electrode surface. Okay. Now this equation up here that we've previously written down, that refers to the derivative of the surface tension versus these quantities that we can measure, is called the electrocapillary equation.